flowing out. So generally, this is going to bring more positive charge in the inside of the cell, generally. Okay, let's talk about that example I was talking about. So let's talk about ion permeability and how that affects various things. So let's say in this example, we're working with sodium, only sodium. And on our x-axis, we have time. So you have our permeability be like this, blah, 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 blah. And suddenly we open the sodium channels up, bam. Our permeability, we'll just leave them open. So we see this sudden change in our permeability. It increased because we're opening up these sodium channels. Well, there's this parameter called conductance. What does conductance mean? Conductance basically means how easily does the membrane conduct this kind of influx of charge. This influx of charge can also be considered as current. And this is kind of getting the idea of how much of this is this membrane acting as a conductor versus an insulator. If the conductance is low, it's going to act more like an insulator. If conductance is high, it's going to be more like that. It's going to be more like water. It's going to be more like a conductor, right? So when that permeability increases for sodium, what do you think is going to happen to conductance? Let's say conductance is here. What do you think is going to happen at this point? Yeah, conductance is going to increase, right? Well, increase right at the same time. Right, it's also conductance is going to change with permeability. Now, so the membrane potential is here. It was at negative 70, right? Millivolts. At this point, when you open up the sodium ion channels, what do you think is going to happen to membrane potential? Yeah, it's going to depolarize. It's going to get closer to zero. And so chances are it's going to look something like this. It won't be gradual, right? It's going to slowly happen, but it's going to eventually reach the sodium ion equilibrium by the Nernst equation. I believe that was just like, I forgot what it was. I'm not going to write a number, but you can go look up the table. It's going to reach that value. This is going to be the equilibrium value for sodium. Now, yeah.
And that's depolarizing?
Thank you for catching that. Thank you, yes. You're absolutely right. It's depolarizing, so it's going the opposite way. It's eventually going to get this value of sodium. Keeping me honest. Thank you. So current. Current is literally called the change of, it's just basically the flow of charge. When you talk about current, you usually think about it like electrical systems, right? As electricity flows through a wire, that flow can be described as a current. So how much electricity, how much electrical charge is flowing through a certain area at any given time. It's a rate. And so that's what current stands for. That's what current really represents. And so this is current. And what do you think current, so let's say current right now is at zero, right? Or close to zero. Not much charge is really moving around the cell membrane because it's mostly an insulator, right? And so for current, generally when positive charges are entering the cell, we consider that a positive charge. So we'll see something like this, where it increases because of positive charge going in. Positive going into the cell. And so it will spike, but then it will eventually level off. It will go back close to zero. And why do you think that's the case? What about the gradient? It's going back to the electrochemical equilibrium, right? It's not going to flow in constantly. It's going to follow that electrochemical gradient that we saw before. So there's going to be this pulse of influx that's going to relate to an increase in the charge, increase into the flux of charge, which is an increase in the current. But that's going to level off as we hit that equilibrium potential, that equilibrium point between the chemical gradient and the electrical gradient. Yeah, let's do this with potassium. Yeah.
Sorry, on the previous slide, whenever you were saying like loop was depolarizing, doesn't it go closer to 0?
Yeah, that's a
So
depolarizing.
wouldn't it be going down?
The membrane potential? So the membrane potential starts at -70, and 0 is somewhere up here, so it's going to go towards 0. So this
Okay,
is,
so then the bottom line is kind of irrelevant?
yeah, this is not representing anything specific. So
Okay.
this is -70 at this point here, and then this is 0. Yeah,
Okay.
these are abstracted graphs. You should not. This is not 0 at this point right there.
Okay.
Yeah. Thanks for that clarification. Okay, let's do the exact same thing with potassium. Just trying to change my colors here. The potassium stiff, and then bam, it opens up. And the conductance of potassium, same thing. Conductance will jump along with the permeability. Now, what do you think is going to, so if this part is in -70, it's going to start here. Sorry, let me just make this dashed line to make everything look even. What do you think is going to happen at this point? Mm-hmm. Because that positive potassium is leaving the cell at this point, and so it's leaving those negative anions or negative proteins still in there, so it's making the inside of the cell more negative. So it's going to reach this with this, and it's going to reach that equilibrium point for potassium, which I remember is -70 from the previous slides. No, -90. Sorry, -90. So yeah, it's going to reach that. And then you can kind of guess where I'm going with this. And this is a chart, this is 0 for the charge. It's going to be something like this. And then instead of a positive charge, because the positive charge is leaving the cell, it's going to be negative. So it's going to look it's going to be like here, and then you see a spike, and it'll eventually come back down like that. So it's the same idea, same thing, but in opposite direction, essentially. All right. Oh, actually, that's the end of class. So we'll pick this up Thursday. We'll learn about gradient potentials and action potentials. You're in my class.